I'm Dan. I'm a data scientist at TrueMotion. So TrueMotion, we develop software that can track how good of a driver you are by leveraging the sensors in your smartphone. We use this information to prorate your car insurance and to improve your driver safety by communicating tips and other pieces of information that we think can help you become a better driver. We're partnered with some of the largest insurance companies in the world, including Progressive and Allianz Insurance. So many of you may have heard of usage-based insurance programs. Some of you may have usage-based insurance programs. They've been around for about 10 years. This is a picture of Progressive's snapshot device. The way this works is you tell Progressive, or Progressive tells you, that you want to sign up for a usage-based insurance program, where your car insurance is going to be prorated based on how much you drive and how well you drive. So Progressive will send you one of these devices, you plug it into your car, you drive around, it will see how much you drive, it'll see how well you drive over the course of a few months, and then you send it back. So this is a good model. The main problem with it is it requires you to get this device, and it requires you to put it into your car, and it requires you to send it back. And there's a lot of steps, and most people don't want to go through all that trouble. So because of that, only about 2% of insurance programs in the United States right now are usage-based insurance. And we thought that if usage-based insurance was as easy as downloading an app, you get the insurance program, you download an app, you don't think about it anymore, and then it just gets factored into your next insurance bill, it would have significantly higher adoption rates. And insurance companies thought so as well, because this is one of the hottest things in insurance. This is actually a really competitive space. We're one of a large number of big players competing for pretty much every big insurance company in the world is launching smartphone-based UBI right now. So what are the important things that a usage-based insurance app needs to do? So the critical component that really is the selling point for smartphone UBI is that there's no user interaction required. You download the app, you don't think about it anymore. If you've got it mounted on your dash, if you've got to press a button every time you start a drive, it's just never gonna work. Nobody's gonna wanna use it, and if you do use it, it's gonna be inaccurate because it's gonna miss a lot of your drives, you're gonna keep forgetting, and it needs to not need any interaction. It also needs to accurately predict how much you drive and how well you drive. It needs to capture dangerous driving behaviors. And one of the hardest problems to solve is that it can't penalize you if you're using public transit or if you're a passenger in a car. I mean, think about how would you prevent that? We'll talk a little bit about some of the strategies you can do to fix that problem. So the first problem that pops up is trip capture. We need to know when you're driving. And you might think, oh, this is a pretty easy problem, right? Your phone's got a GPS in it. Just look, if you're driving over 15 miles per hour, you're driving. Well, we can't exactly drain your GPS 24/7 looking for you to drive and burn all your battery out. So we've got to get kind of smart. So one thing that we can do is take advantage of Wi-Fi locations and cell phone towers that you're nearby. Your phone can see Wi-Fi networks. Your phone can see cell phone towers. It can also see how strong the signals are, and it can see how those signals roll over as you move. And we can use these really low power signals to detect when you're moving. We can get a really rough estimate of your speed and position and know that you're in the process of taking a trip. Okay, so we figured out you're taking a trip. We've done it with using very little battery. The next problem is, what is your mode of transit? Are you taking a bus, or a train, or a bike, or a car? And this is a pretty tough problem. There's a lot of different approaches to solve this problem. There's some really cool papers out there, actually, that this is a pretty hot topic in academia as well, where you can pull out different frequency spectra from the motion sensors in phones based off of the vibrations that are different based on the engines in these vehicles and the sizes of these vehicles and the shapes of these vehicles. I'm not going to talk too much about the mode of transit algorithms. I want to focus a little bit more on driver identification. So driver identification is really hard. There's the key component here is if you were a passenger in a car a lot, we don't want to say that you drive a lot, because your insurance should not reflect the fact that you're driving in someone else's car, and it shouldn't reflect the fact that your friend Larry is a terrible driver. So there's a few different methods that you can use to determine driver and passenger. And one that I want to talk about is car exit door. So if you're a driver in a car, you're almost certainly going to exit from the left side of the vehicle. If you're the passenger in the car, you're usually going to exit from the right side. Not always, but usually. So there's a few different ways that you can build a classifier for right door exit versus left door exit. And one really useful signal is yaw. So for those of you who haven't worked too much with angles or aerodynamics, yaw is it's your angle with respect to gravity. So a yaw diff would be the difference in that angle with respect to gravity. So that looks like this. So a positive yaw diff is going to be a rotation like this. A negative yaw diff is going to be a rotation like this. So you can sort of see, if you're sitting in a car, you get out from the left side, you're going to see that positive yaw diff. You get out from the right side, you're going to see a negative yaw diff. So this trip actually is an Uber trip that I took. I was a passenger in the car. I got out of the right side, my phone was in my pocket, and you can see this negative yaw diff spike, just when the GPS speed reaches about 0. Now this is not so easy. You make it sound easy, but it's not that easy. I mean, maybe your phone is in a backpack, or in your purse, or you're holding it in your hand, or you reach back inside the car and grab it. See, we can't just compute yaw, threshold it, and say we've solved DI. You're not really gonna get far doing that. So you've got to use a machine learning classifier. There's some pretty cool deep learning methods that work pretty well here. And there's always a balance of how much information do I want to provide to the deep learning method, or how much do I want it to suss out by itself? And I'm not going to get too into that, but there's some really cool stuff that's going on in the driver identification space, and a yaw method is just one of them. Okay, so dangerous driving. So one really important part of a usage-based insurance program is being able to detect when people execute dangerous driving maneuvers. So this could include things like hard braking, things like turning fast, things like sidewall skiing, which I think is what this is called. And so there's a bunch of different approaches you can take, and that we do take, to sussing out dangerous driving behaviors. And one that I want to talk about is phone-car alignment. So a car has 3 canonical axes of acceleration. There's the longitudinal acceleration of the car, which is the front-back axis, the lateral acceleration of the car, which is side to side, and the vertical acceleration of the car, which is up down. So a hard brake is essentially just a negative longitudinal acceleration of the car. A sharp turn is a strong lateral acceleration. So if we can pull out these accelerations in the different axes of the car, then we can know when people execute dangerous driving behaviors. Now there's a problem. Your phone has an accelerometer in it that's very useful, but the phone reports accelerations in its axes of rotation, which is its X, Y, and Z axis, defined as such for those of you who haven't worked too much with smartphone accelerometers. So the key problem is we need to find the rotation matrix between the phone and the car. But if you remember from earlier, we can't have the user communicate to us what that angle is. We can't tell the user you need to mount the phone in a particular way. The phone might be in any place at all. It might be in their backpack, it might be in a mount, it might be in their pocket. So sussing this out is not super easy. But there's actually a pretty interesting method that most of you have probably worked with, called PCA, that does a pretty good job at doing this for us. So principal component analysis helps you find the axes of maximal variance in some data. So if you have data on the accelerations that a phone experiences when it's in a car, those accelerations are going to be caused by longitudinal accelerations of the car when it's speeding up or slowing down, or turns of the car, which would be centripetal accelerations, which would be in the lateral axis of the car. So actually, when you project the data points of accelerations experienced by the phone with PCA, you get the longitudinal and lateral axes of acceleration. And that can, just like that, give you the dangerous driving maneuvers. So it looks like I finished pretty early, actually. If anyone's got any questions?